So now we can look at the Bohr model of the hydrogen. So the hydrogen atom. You've probably seen this picture before. So basically Bohr said that the atom is going to have a dense nucleus, when that's where all the positive charge is, and then you have electrons kind of circling on the outside, and then most of the atom is empty space. So right, you had a nucleus here, and then you had these rings of electrons. Maybe you've seen this picture before, right? Probably. So you have electrons kind of occupying here, and electrons can be here. That's great. And what he hypothesized, and this is basically what he did. He did a whole bunch of experiments to try to explain why you see this line spectrum. So how come you don't see a continuous spectrum when you do the experiment with any element? You don't get all the colors out. So if I took, and this is what we're going to do, we're going to do the flame test. If I take a metal and I put it in a flame, the flame's going to turn colors. I'm going to see like one color. How come I don't see a rainbow of colors? So, and it has to do with this idea that electrons are absorbing a certain amount of energy, and they're jumping energy levels. They're going from this orbital to this orbital. And he said that energy is quantized. So an electron can either be here or here. So it can only absorb this much energy, or maybe it can absorb this much energy. But because an electron can't be anywhere in the middle. And that's what this word quantized means. It means there's a limit to how many. There's a discrete set of values that you can have. It's limited. Continuous would be it can have any possible value. It can absorb any amount of energy. It turns out atoms can't. They can only absorb energy here or here, and so that difference is pretty much how the energy that's absorbed. So electrons can be in any of these levels, and the difference between them is how much energy they can absorb. And because each atom has a different electron configuration, has different circles here, different orbitals that its electrons are allowed to be in, each one's going to be able to absorb a different amount of energy, and which is why we only see different colors for different elements. And so when we do the flame test, it's pretty cool because you can actually see these colors. And so when you look at fireworks and things, fireworks are made of a bunch of different metals, and so you can say, oh, if I want purple, then I use this metal. If I want green, I'm going to use this metal. So you can kind of use all those the properties of those metals in the flame test here. So quantize really. So this is trying to show a picture of what quantized energy levels would look like. You can step on this part of the stairs or this part of the stairs, but you can't step in between. If you had a continuous spectrum, or if you had a continuous number, you can step anywhere on this ramp that you want. You can take infinitely small steps. But that's not what happens with the atom. The atom likes to be in its ground state. That means all the electrons are in their lowest energy level possible, so they're as close to the nucleus as they can possibly be. Now you're limited by how many electrons are allowed in each level. So you can only have 2 electrons per orbital, and you may have more orbitals in any given shell. So these are different shells. These different circles are actually energy levels. Different shells, we'll talk about that later. We're not really going to get too into it. But we should know the difference between the ground state and the excited state. So the ground state, all the electrons are in their lowest possible energy level. And then, during the flame test, what you do is you give it enough energy so that one of those electrons gets promoted to a higher energy state. So suppose I had an electron here, and now all of a sudden it's going to absorb a certain amount of energy. Oh, is it not? Oh. It's not writing anymore. So you can absorb a certain amount of energy. It'll go into a higher energy level, and then it's called an excited state. So then you have an excited state here. Oh. All right, and then what happens during the flame test is when that electron falls from the excited state to a lower state, it releases a certain amount of energy, and then you get the emission spectrum. So then you get to see those different colors come out. All right, so here's a picture of that's kind of what I was trying to draw. So here you have your ground state, your electrons are in the lowest energy state, then you absorb a certain amount of energy, it gets promoted to this higher energy state. This is called your excited state, and then it only stays in that excited state for like a fraction of a second. And then it releases energy, it releases that photon, and then you'll be able to see that if it's in the visible spectrum. So if it has the right amount of energy, you'll be able to see it as a color. So you'll see a color change in the flame, and then you go back down to your ground state. So that's kind of what the flame test is all about, and that's about the extent that I want you to be able to describe it. So you start in the ground state, absorb a certain amount of energy to an excited state, and then you release that energy again. That's when you see the color during the emission, it's going to emit a photon when it relaxes back down to its ground state. Every element is going to have a different set of these energy levels. So these are different energy levels, different shell, due to its electron configuration, and so that's why we see different colors. The quantum mechanical model can be described. Here we go. So we have different layers. So we have these 4 quantum numbers, and they're going to describe different things about those orbitals. So the first one tells you about the energy level. Is it close to the nucleus? Then it's at a low energy level. The further away you get from the nucleus, the higher the energy level is going to be. The orbitals, the sublevels will also tell you about the shape. Is it an s orbital, a p orbital, a d orbital? Each one's going to have a different shape. You can see that on the next slide. They're going to have different orientations in space. That's another quantum number that will tell you, they'll be able to tell you about. And again, we're not really going to go into this. We'll talk a lot about this in Chem 1. We're just kind of building up to how to write electron configurations. So we'll get there in a second. So we have our energy levels, and then the S and the P are different shaped orbitals, which are kind of down here. So this is an s orbital, it's spherical. These are p orbitals. Turns out there's 3 p orbitals, and they're shaped like dumbbells. And they have all the p orbitals they have the same shape. They're just in different orientations. And then these are your d orbitals, which kind of look like 2 dumbbells together. All right, and so we have principal energy level that tells you kind of what the energy is. The sublevels are going to tell you kind of what the shape looks like, and then we also have orientation. And then the last quantum number has to do with electrons themselves. So you can kind of answer these questions here. There's no d sublevel when n equals 2. I mean, I'm not even going to worry about these. And my son is crying, so I'm going to stop.